All right, so a couple reminders, and then we'll just jump into the agenda. The mass versus weight lab reports due today, and so a couple of you are already making a pile here on this stool, and you will possibly have a few minutes at the end of the period to kind of get with your lab partners and make sure you're squared away on that. And then the AP classroom assignment, watching those videos and answering those questions, that again is due next Wednesday for you guys since there's no school Monday. So don't forget to be getting the lab report turned in today and doing the AP classroom work for next Wednesday. For the AP classroom work, just make sure you watch the video all the way through. If you stop it early, then it shows me you didn't watch it completely. So the only way I can give you full credit is if it shows me you watched all the way through. So let it run to the end. Don't stop it when they start the closing thoughts. And then for the questions, it's not how many you get out of 12, it's that I can see you invested a reasonable amount of time. So if you spent 30 seconds on 12 questions, that's not a reasonable amount of time to get anything out of it. So I'm looking just to see that hopefully you get them all right, or many of them right. They're difficult, so not that many students will probably get them all right, but some will. But I'm not looking necessarily for a perfect grade, but I am looking for an investment of time, that you're taking the time to actually go through it. Any questions about the assignments? All right, so we are going to, yeah, go ahead.
If we're online, how should we submit the lab?
For the lab, for those of you that are virtual, it's probably better just to wait and turn it in when you get back.
Okay.
You could scan it, but then you also have to scan the table of contents and all that. That's probably not worth the effort for that. Just bring it in when you're back.
Okay.
And if you want to send it scan-wise, that's okay, but I won't count it late for those of you that have been out.
Could you also just take a picture of it?
Yeah, picture or scan, but you would still have to do not only the report, but also the table of contents so I can see, and so probably easier to just turn in later. All right, any other questions about that? All right, so today's goals, we are going to review tension force, which we've talked quite a bit about, and I doubt if you have much concern about tension force, but we're going to compare it into a system. As we've been going through gravitation and thinking about moons and planets and satellites and how there's multiple objects at once and multiple forces at once, one of the things that I've noticed is a lot of students really struggled with the question that had to do with a system of equations. The one where they had the Earth and the Moon and the spacecraft in the middle, and you had to kind of use a system of equations to solve it. And so I thought, you know what, we should actually do another type of system just to practice forces one more time, because this type of system of forces is pretty common. I wouldn't say I could guarantee it's going to be on the test this year, but I would be pretty surprised if there wasn't at least a question like what we're going to practice today on the May exam. And so it'd be a good chance to practice kind of two things: reviewing forces, systems of equations, all that good stuff. All right, after we've reviewed that, then I've got an FRQ that we're going to practice from the 2015 exam that is very similar to what we'll go over. And then if there's any time, we'll start to preview a few things with circular motion. I have a couple of simple demos and videos to kind of get you thinking about that if there's time. All right, so let's jump in. Oh, actually, if you haven't picked up your graded work over here on the side, there's some papers that are graded. If you didn't grab that already, go ahead and do that while I get the attendance recorded on Axis.
Yeah, worksheet.
All right, So here is the kind of system that is typical. Oh, there's Ashley. All right, thanks for the note, Bennett. So here's the kind of system that is pretty typically shown as a straight up force. So not so much about gravity, but just another kind of system where you've got multiple objects creating different kinds of forces, and to solve it, you often need some sort of system of equations approach, whether it's, there's a couple different ways to do it. I'm going to show you two sort of strategies to use a system of equations, and you can decide which one would fit your process of thinking best, your problem solving process best. So we call this kind of device an Atwood machine, and it can look a lot different. It can have multiple weights, multiple pulleys. This is like the simplest version you could see, a single pulley with two weights. And there's a couple things that are interesting about these machines, and I think that's why they use them on tests a lot. One is that if there's only one rope, the tension in that rope will be the same all throughout. And so that's a nice problem-solving bit of data, and understanding that if there's only one rope, the tension is the same throughout, makes it easier to solve. Now again, you will see some scenarios where there's multiple ropes, multiple objects. It can get more complicated, but we'll start with a simple move or a simple example. Also, if two masses are hanging down from either side, there's going to be some movement though. Like even though the tension's the same, there's going to be some movement. So if I set this up and I put the 50 kilogram mass on one side and the 20 kilogram mass on the other, and then I let go, what's going to happen? Yeah, the 50 is going to go down, the 20 is going to go up, and it's going to rotate around the pulley, right? I mean, pretty logical what's going to happen. And so, will there be acceleration? Yeah, because the thing that causes the motion is the difference in their weights. Since their weights are different, that means there must be a net force. If there is a net force, there has to be an acceleration. So there will be an acceleration in this scenario. But the tension that's in the rope is going to be the same on both sides of the pulley, right? So a couple things to keep in mind. Let's keep moving and start looking at an example specifically of what they might ask. So in this scenario, same picture, 20 kilogram mass hanging on one side, 50 kilogram mass hanging on another side. Notice it says that the rope passes over a small frictionless pulley. So you'll typically see words like that. Sometimes they phrase it a little different. They might say the small pulley with zero friction, or they might say with negligible friction, or they might say with negligible mass. They'll often also explain that the rope has negligible mass, because if the rope had significant mass, then you would have a changing amount of weight on each side of the pulley constantly. You need calculus to solve something like that, because as this falls, this part of the rope gets longer and therefore heavier, and this gets shorter and therefore lighter, so you have a constantly changing force imbalance. So they'll usually say the rope is also negligible mass, or they'll say it's lightweight or something like that. Because this is an algebra-based course, so they're not expecting you to use calculus to solve something that's changing like that. All right, so just to be aware of the wording you'll probably see. And then we've got the 50 kilogram mass suspended on the other side. What is the tension in the rope? They might ask what the tension is, they might ask what the acceleration is, they can ask lots of different things, but those are probably the two most common. So we're going to eventually find out what the tension in the rope is. Now, we've already kind of answered this, but which way will the 20 kilogram mass accelerate? Upward. And the 50 kilogram mass? Downward. So typically these are the 6 steps that you would have to work through, not necessarily like memorizing the steps or anything, but the kinds of things you're going to have to do. So one, we should draw a free body diagram for each mass so we can try to figure out what the force and balance is, not only for the system, but for each mass. And then we're going to need to write some net force equations because it will accelerate, so we'll have a net force. And then we're going to have to eventually find some equations for tension because that's what they want us to discover. What is the tension? And we're probably gonna have to find the acceleration along the way. And so there's other ways to solve it, but algebraically, they get pretty more complicated than if we just find the acceleration first and then plug it in. If you're really good at algebra and really good at systems of equations, then I'll mention another way you could approach it, but it definitely takes some strong algebra skills. And then once we have the value for acceleration, then we can plug it in to find the tension force. So this is just like mapping out a strategy. I don't think it's worth like writing down these 6 steps because they might slightly change depending on how the question's worded and what they ask, but just sort of a logical flow here. So you'll see the letters showing up on the slides step by step to kind of remind you of the flow. So the first thing I want you to do is draw free body diagrams for each of the masses, the 20 kilogram mass and the 50 kilogram mass. So whether you do it in your notes or on a piece of scrap paper, if you would rather do it on a whiteboard, if you like using the whiteboards to write it out, we're going to go through all the steps, and I would encourage you to write it so that, one, you have it to look back at as you're solving the free response question we're going to look at here later. And then also just as you're writing, it just keeps you more mentally engaged than if you're just listening only. All right, so go ahead and draw the free body diagrams, one for the 20 kilogram mass, one for the 50, and in about 30 seconds, we'll see what you came up with. All right, how many forces are on the 20 kilogram mass? 2 forces, and they are
Tension,
tension
gravity.
and weight force or gravity. So gravitational force or weight and tension. Okay, so are they equal? Are they unbalanced?
Unbalanced.
Unbalanced. Which one's bigger?
For the 20 kilogram, it's gonna be higher tension force, whereas for the 50 kilogram, it's gonna be a higher gravity force.
Very good. Do you have a question, Quinn, or?
Yeah, I was just asking if ft of 1 it's equal to ft of 2.
Mhm.
Are they 2 separate tensions, or because it's like separated by the pulley?
It's still one solid rope. It's not like,
Well, I mean, yeah, I know that, but like, are you measuring the tension on one side of the pulley versus on the other side?
they'll be equal.
I mean, they'll be equal, but like, it's not for the entire rope, it's for like the 2 sections of the rope. Like the tensions,
In terms of the free body diagrams?
yeah, or no, like, so what I'm saying is, like, is it tension for the entire rope, or tension versus one side of the rope and the other side of half the rope?
Well, you could talk about it either way, but the value will be equal no matter how you talk about it.
Okay.
So if you're comparing left versus right, say it's 200 or whatever, it's going to be the same on the left as it is on the right. Even as that changes, the tension's going to stay the same.
Well, I mean, if you added them, would like the tension be double? Like,
Yeah,
Okay.
because they're always going to be equal. Yeah, but they're not going to. Yeah, so if we find the tension that the 50 kilogram block experiences, that's the same as the tension the 20 kilogram block experiences, and it would also be the same anywhere in that rope, no matter where we measured it.
okay.
So if we think about the free body diagram, sounds like you guys came up with this solution here. We have larger tension on this one and a smaller weight, and here we have a tension with a larger weight, and these tensions have to be the same. So hopefully you drew those 2 tensions the same length, right? The tension on this side should be the same length as the tension on that side. The weight of this one is obviously less than the weight of that one. All right? Any questions about the free body diagrams?
So the force tension should be equal for both?
Yes. Because it's one rope, so If it's all one rope, then it has to experience the same tension at any one point.
And what would happen if it didn't?
It's impossible for a single rope to experience a different tension in different spots unless it's connected to different objects. So if it's just one rope with nothing, no breaks in it and no other objects connected in the middle, it will always be the same throughout. All right, so the tension in the rope says down here, remember the tension in the rope is the same everywhere. So the tension for object 1 is the same as for object 2. The direction of the acceleration obviously is different. We've shown in the free body diagrams that the one is going to be accelerating upward and the other is going to be accelerating downward. But what about the magnitude of the acceleration? We said the tension's the same, but would they accelerate the same?
Well, because they're both connected to the same rope and the rope can only move one direction or the other, one would think that they would have to have the same magnitude of acceleration.
Yeah, that's good. They do for exactly that reason. Since they're connected, if one was accelerating more than the other, the rope would either have to stretch or get slack or something but that wouldn't naturally happen, right? If there's no malfunction or some weird thing going on, the rope should just stay tight and they should just rotate, like the two objects just move, right? So while the accelerations are pointing in opposite directions, they're connected, so they should each accelerate the same value. All right, any questions about that? All right, so step B, if we're kind of, and again, I don't know that I would memorize the steps, but this is just how they laid them out. Step B, write the net force equation for each mass. Remember, there's no special equation for tension. We just call it tension and we're just going to be relating it to the net force. We need to use the net force to find the tension. All right, below each diagram, write the net force equation for each mass. All right, so if we look at the green one on the left, the 20 kilogram object, let's see if we can come up with some net force equations. So how would we calculate the net force for this one here on the left?
We do net force equals tension force minus the gravity force of mass 1.
Yeah, so here they've labeled tension force Ft, and for the weight force or the force of gravity, they've just called it M1G. That's how you would calculate it, right? So instead of abbreviating it FG, they've just done M1G, and a lot of times College Board actually has that on their scoring guides. So let's just go ahead for today, let's just use that. It would be fine if you called it FG1, but we'll just use this because that's actually how we're going to need to calculate it later anyway. Well, what's another way to calculate net force? According to Newton's laws?
Oh, I thought it had something to do with using the force coefficient.
For friction, if there was friction, that might factor in, but what did you say? Yeah, the other way to write the net force is just the mass, in this case of object 1, times the acceleration that object experiences. So we kind of have a system of equations here, right? We got two equations for net force. We can set them equal to each other, right? So M1A has to equal the tension force minus the weight of box 1. So let's keep that in mind here. Now for College Board, you could show, I'm kind of writing every step that we think through. You could jump straight to here. Okay, this is net force, this is net force. You don't have to show these two equations. If you're able to logically jump to here, that would be okay. But because we haven't talked about situations like this in a while, I thought it'd be good to kind of refresh your memory that generally speaking with net force, we can find it multiple ways. And for this scenario, these are two different ways we could find it for box 1. All right, let's see if we can do that for box 2 then. What's the net force for box 2?
Net force equals either the mass of object 2 times gravity, or I'm sorry, tension force minus the mass of object, well, no, I'm sorry, we'd do massive object 2 times gravity minus force of tension.
Mhm.
Or we could do massive object 2 times acceleration.
Good.
And so smart.
Is it okay if I just skip this step and just go ahead and put in MA? Are we okay with that? Just not write this down on that one? Not too confusing. All right. So M2G minus the tension. All right. So now we've got two equations, one for block 1 and one for block 2. They both have A. Are the values of A in these two scenarios the same?
Yes,
Yeah. They both have tension force. Are the values for tension force the same?
yes.
So now we've got two equations that have some variables that are alike and some variables that are different in terms of their order, but they all include the same variables. So we should be able to use these as a system of equations, right?
Yes.
We don't know A and we don't know FT. We need to find FT eventually. So we could use elimination, we could use substitution, however we would want to go about that, we can do that. Now, if we wanted to cancel out acceleration and just directly solve for tension force, that's possible. But because acceleration is being multiplied by something, we're gonna end up with a fraction, and then when you substitute and do some removing, you're gonna end up with a fraction inside of a fraction. And so it starts getting kind of messy. Not impossible by any means, but the algebra becomes a little bit trickier, right? Since tension force isn't multiplied by anything, if we eliminate tension force, that's gonna be a little easier algebraically. Just gonna take a little bit less mental work to do that. That making sense? Because it's just a single variable. And if you look at these, you notice in this one, it's positive, and in that one, it's negative. So if we think about elimination, we can just add them together and they're gonna cancel, right? So that should be a pretty simple way to combine them. So while we could solve either of these for A and then substitute, it gets a little messy, so let's go the easier route and let's combine them in a way that solves or eliminates FT so we can just find the acceleration. All right, so here you can see what I was trying to mention. Now we've got these same two equations. So if I took this one and I took this one, and thinking back to your math class, if we added these together, you see how the tension force just cancels. And so in the end, we would end up with M2G minus M1G equals M1A plus M2A, just adding them together vertically. Everybody tracking?
And we know the gravitational constant, right?
Yeah, we know G, and we know M1 and we know M2, so we would know everything but A, right?
Mm-hmm.
So that's kind of handy. So you could use elimination and just add them together. If you didn't notice that, they show substitution, so I'll show that on the next slide. If you don't like the elimination strategy, I'll show you how the substitution gives you the same result. But I'll give you a few seconds for those that are jotting some things down here. I'm guessing most of you are probably equally confident doing elimination versus substitution, but maybe not. I mean, some students just don't like the elimination, like that vertical adding and subtracting deal. So I won't go through every step of it, but I'll at least show you how you could get the same answer using substitution, because they've worked it all out on here for us. So basically, they're saying I could solve this one for FT. So just add M1G to the other side, and then I can substitute this in over here. Right, so you can just isolate FT and then substitute it into the other one, and you end up getting the same thing. Right, so we're still gonna get this same equation, but just solving for FT on one of them and then substituting it in on the other. All right, either way, same result. Whichever way you feel more confident with is the way I would suggest. I mean, to me, elimination looks a little easier, but not much different. So any questions about the combining the two? as a system to eliminate one of the variables? Right, so as we look at this equation, whether we found it with elimination or whether we found it with substitution, this equation here at the bottom, do we know M1?
Yes,
20 kilograms. Do we know G?
yes,
9.8. Do we know M2?
yes.
50 kilograms. The only thing we don't know is A. So we've got it down to only a single variable. Now, we do have A's on both sides of the equal sign, so how are we gonna isolate A when there's two of them here?
You just divide by, let's say you wanna get, A on the left side, so it's positive. You just divide by, mass one and then by gravity, or the gravitational constant.
So divide M1 and G.
Yeah.
Well, here we're adding those.
Take M1 out,
Say that again.
take M1 out and then M2 out.
Take M1 out on this side and M2 out on that side?
Yeah.
We could do that.
You get it to one side, so it's M1 times A plus M2 times A is equal to M2G minus M1G, and then factor
Yeah.
out A.
Yeah.
Just subtract M1.
It takes a couple steps, but I think the easier way algebraically is to get the A's on the same side first before we do anything else, and then it becomes a little bit easier. So let's show you those steps. All right, so we've got them combined here, so we've already got that taken care of. So here's our result. So you can see how they just added the M2A to this side, and then they subtracted the M1G from that side, so the A's are on the same side of the equal sign. They've just added and subtracted to go from here to here. Everybody following that okay? All right. And once we have the A's on the same side, then we can factor them out. And so now we just have a single A. So I think that's probably algebraically the easiest way, is to get them on the same side, then factor it out so there's only one of them. And then we're going to divide both sides by this sum so that the A is isolated. So get the A's on the same side of the equal sign, factor them out, and then divide to isolate the A. So any questions about this step here, the algebra behind how we're getting the A isolated? All right, well, go ahead and, we know these numbers, right? We know mass 2, we know mass 1, we know G. So go ahead and find out what is the acceleration. Go ahead and plug in your numbers with your calculator and solve for A. For those in the Zoom, once you figured out what A is, just type it in the chat. And for those in here, when you've got an answer for A, just raise your hand briefly so I can see timing wise. In here, how many have an answer for A so far? Just 1, 2? Okay, maybe a little more time. Again, for those of you on Zoom, if you have an answer for A, just type it in the chat. Let us know what you came up with. We got one answer on the chat now. How many in the room have it? Okay, we got a few more now. What did you get, Brendan?
4.204.
4.2. All right, we got a couple 4.2s in the chat as well.
Big brains.
So let's take a look at that.
So smart.
So just plugging in the numbers, 50 times 9.8 minus 20 times 9.8 over 20 plus 50, we should get 4.2 meters per second squared. So that's the acceleration of the 20 kilogram mass going upwards. It's also the acceleration of the 50 kilogram mass going downward. Now to do that, it wasn't super tricky, but we had to think about two different ways to solve for F net for box 1 and put those together, and two different ways to solve for F net for box 2 and put those together, and then take those two separate equations and combine them as a system. So it was, quite a few different equations to pull ourselves together with that. It wasn't hard mathematically, but it was quite a few steps, right? I mean, lots of equations to look at. I'm going to show you what I usually do. It's going to abbreviate that process significantly, right? It may or may not be super clear. Some of you will see it right away. Oh yeah, that makes sense. I got it. And if it does make sense to you, what it'll do is just make the problems a little quicker for you to solve when you're taking a test, okay? If it doesn't, you can always use this sort of systems approach. This will work. Just isolate each problem, each object, and then figure out how you can combine them to eliminate a variable. It's not difficult to do either way, but I am going to show you an alternate way that we can still get this 4.2 value quicker. All right. Any questions about this process though before I show you the other option? All right, let's take a look. I call this a system approach, but when I say that, I don't mean like a system of equations. That's what we just did. What I'm saying is I'm looking at this whole thing as a total system, like it's almost one object instead of piece by piece, okay? So I'm thinking about the net force of the whole thing, not just one side or the other. The net force on the whole thing would be the mass of the whole thing times its acceleration. A question: would the acceleration of the whole thing be the same as the acceleration of block 1 and block 2? Yeah. If block 1 is accelerating up at 4.2, block 2 has to be accelerating down at 4.2, so the whole system is accelerating at 4.2. So instead of looking at the two blocks separately, I'm looking at it as a global group of objects. The net force would be their total mass times their acceleration. Now, I don't know the net force, and I don't know the acceleration, but I do know the total mass. That's just 70 kilograms, right? Just add them together. I also know that the net force is caused by this weight being larger than that weight, right? So instead of thinking about the tension, I can just say, well, this weight pulls that one, so the net force would also be this weight minus that weight, because that's what causes the motion. So instead of looking at block by block, I'm looking at it more globally. The whole thing accelerates a certain amount based on its whole mass, and the whole thing moves because of the differences in those two weights. So I found the net force two different ways. The advantage is now I don't have a set of equations for block 1 and a set of equations for block 2. I just have a set of equations for the whole thing, and I can go straight to solving for A now. I don't have to do the whole next step of systems. So if I set those two equal to each other, total mass times acceleration equals the weight of 2 minus the weight of 1. Do I know the total mass? I can find the weight of 2, 50 times 9.8, weight of 1, 20 times 9.8, and solve for A. So it's much quicker if I think of the whole system as one object instead of separate pieces. So it's just an alternate way to approach it. And we still come up with the same 4.2 meters per second squared of acceleration. Since they're all connected, they have to have the same acceleration. Now the directions obviously are different, but magnitude-wise, it has to be the same. So either way, we get 4.2 meters per second squared. Any questions about this approach? It's a little different. Looking at it as a bigger single system instead of individual parts. right, so you can decide which approach makes more sense to you whenever you're solving a problem. In a few minutes here, we're gonna have you try an FRQ from College Board from the 2015 test. And if you like that original approach we took, where you look at object 1, object 2, make some systems, pull them together, by all means, that works. If you think this makes sense, looking at it more globally, that works as well. In fact, on the scoring guide, they show you both ways. Okay? All right, let's go ahead and, we're not actually finished with this question though, because what did the question ask us to find? Tension, and we found the acceleration 2 different ways, but we haven't actually found the tension yet. So we need to do one little bit more. So let's go ahead and see how we find the tension. So now we know the acceleration is 4.2, right? We solved it 2 different ways, so we know that to be true. And to find the tension, we can just pick box 1 or box 2, it doesn't matter. And we can come up with an equation. The net force is going to be the tension minus the weight. We talked about that the previous way, which means M times A is tension minus weight. We know the mass. We found the acceleration to be 4.2. We know the weight, so we can find the tension. So either way you did the first part, this is how you would finish it. Right? Whether you found the 4.2 by that multiple systems approach or a global system approach, you're going to end up getting the acceleration, which you're just going to use to find the tension this way. So any questions on this step of how we take that acceleration and then determine what the tension in the cable is?
May I please have the FRQ?
In a few seconds.
Okay. Ready, please?
Yep, the answer's still the same.
Okay.
All right, now I do want to just briefly show you that, just kind of to prove, if you chose to do box 2 to find this tension, you'll get the same answer. So you don't need to do both unless you just want to prove it to yourself, but if we focus on box 2, that net force was weight minus tension. And if we plug those numbers in, we still get 280. So once you get to this point and you know the acceleration, since they both accelerate the same, you can find the tension from either box. Doesn't really matter which one you choose.
I don't really like where you focus on box 2 because then you end up having force tension initially as a negative.
Yeah, I would probably pick box 1 myself, but both work. All right, any questions? All right, well, let's go ahead and get you started on this FRQ. It is from 2015, so briefly, let me show you, for those on Zoom, let me show you where to find it. So on Axis, I got logged out here. Slow. All right, so on Axis, let's go to section 4, Physics 1 AP. If you go to topics, you'll find this FRQ in Unit 2C. Unit 2C, unbalanced force model, right down here. And it's just over here on the bottom right. It's FRQ number 1 from 2015, and then the scoring guide is right underneath it. All right, so the question, what's that? Well, you're gonna get 15 minutes to try it.
Uh-oh, I think it might be late. Can I use one of my grace assignment things on it?
Not on this one. It's not homework, it's classwork.
Unlucky. I swear.
Okay.
Washed away.
All right, so this FRQ, whether you're seeing it on Axis or whether you're getting this paper copy from me, if you look at the directions are more global for the whole exam, which you don't have, you just have this question. But it says this question's worth 7 points and suggested time of 13 minutes. So we'll go till, 13 minutes will be at about 10:55. So I'll give you till 10:55. And then we'll have you check it. So good luck. I would like you to try it on your own. I know obviously if you're at home on Zoom, you kind of have to, but in here, I'd like you to try it on your own, see if you can figure it out, and then I'll give you a chance to discuss it afterwards. All right. So you've had about 13 minutes to answer the questions. For those of you that are on Zoom, the scoring guideline is right underneath the link where you found this, so you can open that up and self-score, and then we'll take a time for questions. For those of you in here, I did print it for you, so you can score your own page. At this point, you're more than welcome to converse with the other students and see, even grade each other's if you want, or however you want to look at it. And then after a few minutes, we'll go over it together.
Is it 13 minutes per SAQ?
It's different from question to question, so you have 3 short ones and 2 long ones, and, so depending on the nature of the question, the timing suggested can be different.
So any change in mass would have caused a change in acceleration, not necessarily no friction, meaning no change.
Correct.
So even, okay. So even though, let's say you put on like a couple grains of sand into the mechanism, it would still cause, even microscopically, a change in acceleration.
Yeah.
So besides mass and friction, what else can change the acceleration?
Those would be the 2 most common things that they would use, because it's easy to just add another object into the system or to say there is friction. So those are the 2 most common. Trying to think of anything else I can recall them using. I was actually going to mention later that friction is one they'll sometimes throw in, but other than adding objects and friction, I can't think of anything right now that I've seen them say otherwise that would change it.
I mean, I guess you could say maybe air resistance.
Haven't seen that because it would be pretty negligible, things moving this slow. But yeah, I mean, I suppose they could say something about drag, but I've not seen that. Yeah, Griffin?
If I use the method that you showed, the second method where you use the mass of the whole system, would I still get full credit because it says that you need to write the equation for block 1?
Yeah,
On
on
the
the,
second
yeah, on the back it shows the alternate, which is what I used, or similar to what I used.
Okay.
Give just another minute or 2 to kind of glance it over, self-score, and then I want to make a few comments about it as well.
For B, I didn't separate gravity from M2 and M1.
That's fine.
Okay. This route, like those average there, like it's law of large numbers.
Say it again.
Like the law of large numbers, it's quite nicely.
Oh.
Yeah, it's like the one with the most items, 99.1, 9.1, 8.66 is the closest to.
But your group was the closest. All right, so just a couple quick comments, and then any questions you have, I'm glad to answer. So on part A, it says that you can get 1 point for drawing 2 vectors on the dots pointing upward that have the same length, and somehow you've labeled it tension force. So they literally just wrote the word tension on the key, but I would probably have done F sub T. It's fine, either way. Those are 2 common ways to, or just capital T would also be okay. And then another point for drawing two vectors starting on the dots that point downward, where the vector for block 1 is smaller and the vector for block 2 is larger, and they are gravitational force or weight. So you could use the word weight, you could use M1G and M2G, you can do FG1 and FG2. You can't use just G. Okay, if you remember that video we watched a while back, that is not an acceptable one. You cannot use just G, okay?
Is it okay that I didn't distinguish between the two? I just put F of G and F of G?
You do need to have them distinguished. Well,
Okay. But I showed different arrow lengths.
yeah, I think since it's visual this time, they would probably let that slide,
Okay.
because the length, I think, is more important. It does say that you would have a point deducted if you have any extra arrows. So if you had 2 extra arrows, you would lose 2 points, which means you'd get a 0. Now you can't get a negative score. So if you had 3 extra arrows, you're not going to get a -1, but you can only lose 2 points. But if you had extra forces, that would take a point off for each extra force you drew. And then the last one, a point can be deducted if your lengths don't show that there would be an acceleration. So if you made them all match, you would automatically lose a point. Or if they all somehow balanced out, even if they didn't balance in the way you drew them initially, but then they wouldn't balance, or they would balance out totally, that would be a deduction. It would be, I think, hard to do that, but someone must have, otherwise they wouldn't have put that exception. All right, any questions on part A, free body diagrams? Yeah, Quinn?
Oh wait, no.
All right. For part B, yeah, Chris?
Oh, I had a question. So for the practice one we did draw in acceleration arrows, but for this one you don't have to or something. Or you want to deduct it?
If you drew an acceleration arrow over here and clearly labeled it A, because then it's not coming from the dot.
Okay.
Yeah. So you'll notice here it says starting on the dots. So if your forces don't start on the dots, you wouldn't get the points for it. But if you have an acceleration vector over to the side, you'd be okay.
All right. Thank you.
Yep. All right, and then for part B, it says you can get 1 point for writing an equation for Newton's second law based on the first block. The net force is the tension minus the weight. Another point for writing Newton's second law for the second block. The net force is the weight minus the tension. And then another point for showing through elimination or substitution or however that you canceled out the tension and isolated the A. So here it looks like, what did they do? It looks like they did substitution. But you could use any method you want.
I just used the simple method, so I just found the net force, which was Fg on 2 minus Fg on 1.
The alternate solution?
Oh, and there's an alternate solution?
Yes, but
My bad, I didn't see that.
looking at the paper.
I was looking at one side and I thought it was done.
That's all right. Yeah, so they do also show on this rubric an alternate solution, which more lines up with the way I would have done it. And in this first statement, they just make a statement. The system of 2 blocks must move as a unit. So the acceleration of the system is the acceleration of block 2. You wouldn't have to write that. That's just a statement to help you understand why they took this approach. And then so you could get 1 point for an equation showing that the net force is the weight of object 2 minus the weight of object 1. They factored the G out. You don't have to. You could leave it distributed. So M2G minus M1G, that's fine. And then another point for writing the equation that shows the sum of the masses and the acceleration of the system. So that's again the approach I took, adding them together times their acceleration. And then the third point for combining those and solving for A. So either approach is fine. They actually on this rubric give both. And just to ease your concern, if you have any, when we grade these, my group will grade thousands of questions. So I might have 15 or 20 teachers in my group. In my group, just meaning that's the group I'm a part of, not that it's my group, but in our group, there'll be 15 or 20 of us. We're grading one question. Each of us is grading maybe 800 to 1,000 of them. And so we're grading the same question over and over and over again. And we're all, in the old days, we would be in a building together. Now we're all on Zoom or we chat through our phones or whatever. And so if I see someone that comes up with a strategy and I think, oh, that actually works, and it's just not part of the rubric, then I write to the committee and say, hey, this student has this. I think they should earn full credit. What do you think? So it's never on the shoulders of one teacher. And there's always some overlap as well. So, and there's also always one teacher who's chosen as the coordinator from the group, and they have to they don't grade any of their own. They grade like 10% of everybody else's. Like, so there's at least, everyone gets graded at least twice, and then it factors in how the two grades are. So there's a lot of safety nets in there. If you came up with a unique strategy, it will probably not get deducted if it makes sense, as long as it's clear and accurate, obviously. So any questions on part B, how to derive the equation for acceleration? All right, for part C, I mainly want to show you this one in case there's questions, but also because this is sometimes how College Board's rubrics get kind of funky, and it's not that uncommon. So you can see that the question says, hey, if you throw that other block in, does that change the acceleration or not? And the answer is yes, it makes the acceleration smaller. But notice, you get no points for saying that. You have to say it, but you don't get a point for saying it. That's the tricky, weird thing. Because down here it says, no points are earned for an incorrect prediction regardless of the explanation, and no points are earned for a correct prediction without the explanation. So if you never say it's smaller, you can't get the points. And if you don't say why it's smaller, you can't get the points. So you have to say it's smaller, but you only get points for the explanation. So it's kind of a weird thing where you have to say something, but that's not what earns you the points. Here's the explanations. So one way would be to say the mass of the system is now larger because it's got that third block in it, and then indicate some way that that would increase the tension in the cable connected to block 2, because now block 2 doesn't have to just pull block 1, it's got to pull block 3 also. It's got to pull both of them. So the tension is going to be larger. So you could take that route. Another way would be still to say that the mass is larger for the whole system, and then talk about it more with Newton's second law. So I'm going to actually write that on here because if we think about F equals ma, what causes, let me show the picture actually again. We can talk about it while we're looking at the picture. There's a third block here, but what causes the system to move?
Net force between F1, M1, and then 2.
Yeah, the difference between this one and this one, right? Since there's no friction, the net force is just this minus that, weight-wise. The weight of this minus the weight of that. Is that any different than the previous problem? No. So the net force, on this one is the same as it was before, right? Nothing changed that way. Since there's no friction, it's still just the weight of this minus the weight of that. But if we think about net force as m times a, what happened to the mass of the system?
It went up.
It went up. Therefore, the acceleration must go down to keep that the same. All right? So if you recognize that this doesn't affect the net force, it only affects the acceleration. That's kind of the alternate solution they're mentioning there on the rubric. That's what they're saying, is you could take that logical approach to explain it too. Yeah, Griffin?
Do they give like half points if you get, no?
No. Now, and sometimes there's this funky wording in the rubric that'll say, you get a point for this, and then it'll say at the bottom, unless they made a wrong statement. And so like, it can negate, not everything, but it can negate like a key point. So if you had everything right, and then at the very end you said something wrong, even if it was sort of irrelevant, if it's a false statement, it takes that point away. Yeah.
So for part C, I said something wrong initially that I still have on my paper, but then I have the other 2 points that they.
So what was it that you said that was wrong?
So I said like the addition of block 3 means the mass difference between max 2 and max 1 will decrease, but then I say the force of weight difference remains the same, but has to move the greater mass.
Mm-hmm.
And so according to Newton's second law, this will decrease acceleration.
Okay, so let's look at the rubric and see how that would score. So, wrong one. So you've said the 2 things, but it says no points earned for incorrect prediction. You got the correction. You said it was less, right?
Yeah.
Okay, and so that's not going to deduct. No points are earned for a correct prediction without a reasonable attempt. So you gave a reasonable attempt. In fact, you said it was smaller, and you gave. So this one, the way it's worded, you would not lose a point for that false statement.
Okay.
But on some of the rubrics, it literally says in there, deduct a point, or unless they made a false statement, something like that. So
It'd be very nice if College Board could make up his mind as to what it wants.
yeah,
I mean, that just makes no sense, like, it's either, okay, they make a wrong statement, but we're not gonna take points, or they made a wrong statement, no point.
Yeah,
Can we have like one or the other?
I think the reason it often is that way is because they have so many hundreds of different questions. And so one question, they want the points awarded a certain way, and then in the end, they realize, oh, if we do that, then it's 1 point short or 1 point too many, and so they have to trim it down, and it ends up making them all the same. It would, yes, be nice if they were consistent, but the reality is they aren't, so. You'll see some patterns, but it's not, none of them seem to be like 100% of the time, so. As you're practicing, I think it's just as valuable to practice answering FRQs as it is to read scoring guides. Because the more scoring guides you read, it's like, oh, okay, I'm starting to see some trends. They often ask this kind of thing, or they often want this, or they often deduct questions. You probably won't find they always do anything, but you'll find some trends where they tend to do one thing over another. All right, any questions on the FRQ? All right, so I'll go ahead and stop the share here. And we have about 10 minutes left, and then we have assembly together. So for those of you on Zoom, did you get a link to the assembly? Tyler did? Okay, I see a few people now. Okay, good. So since you have your own link, you are welcome to hang around if you have questions for me. But if not, you can just make sure for the lab, I forget, I think someone may have asked this, but for the lab, if you want to scan it in and email it to me, you can, but if you want, just wait and turn it in when you come back. That's fine, I won't count it late. All right. So if you want to stick around, if you have any questions, let me know, that's fine. Otherwise, you can be dismissed and just join the assembly on your own link. All right, have a good weekend.